Okay, in this video we're going to talk about inductive reasoning, conjectures, counterexamples. So let's start off with inductive reasoning. What is inductive reasoning? It's a type of reasoning that allows you to reach conclusions based on a pattern of specific examples or past events. Okay, so you can think of inductive reasoning as going from a given pattern, from a known pattern, and then coming up with a rule or with a conclusion based on that pattern. Okay, that rule or conclusion is called a conjecture. So a conjecture is a conclusion reached by using inductive reasoning. Let's look at a series of examples here using inductive reasoning to come up with conjectures. Okay, first example. We want to find the next two terms in this sequence. And we're given 2, 4, 6, 8. Okay, so we're given a pattern here. And we want to come up with two terms. We also want to describe the pattern once we've reasoned through what it is and found the next two terms. So 2, 4, 6, 8, 10, 12 have to be the next two terms. So how do we get to 10 and 12? What is the pattern? We can think about it in a couple different ways. There's not always one set answer or one set rule. One way you can think of it is, well, it's the even numbers. You've learned the even numbers since elementary school. Start off with 2, 4, 6, 8, 10, 12, and they go on and on and on. Okay, the even numbers come from just adding 2 to the previous number. So that's another way to describe it. To get the next term in the sequence, just add 2 to that previous term and you'll get the next one. Okay, so we've got our given pattern, our conjecture, and our rule. Okay, another example. It says find the next two terms in the sequence. Okay, another sequence here. And you might be thinking, Mr. Flory, I thought this was a geometry class. Why are we dealing with all these just numbers that looks like algebra? Well, inductive reasoning is a huge part of geometry and life, really. So what we're doing with inductive reasoning is essential for geometry. We're not just going to be talking about circles, triangles, and squares, and lines, and that kind of stuff. I really want you to get from this class reasoning skills, to where if you see a certain diagram, then you'll be able to use your reasoning skills to come up with conjectures and other information, maybe that's not given directly in the diagram or in the picture or whatever. So there's a lot of logic, a lot of reasoning in this class, and it's going to be essential that you use that throughout the semester. Now, I don't want to turn you into logical robots that just use logic and reasoning, but I want it to be a tool that's available to you to use it when necessary. Okay, example 2. Next two terms in the sequence. We've got 1, 2, 4, 7, 11, 16, 22, and so on. We want the next two terms. Well, we can start off kind of like the last one. Last one, in example 1, we added 2 to the previous one. So if we go from 1 to 2, we add 1. 1 plus 1 is 2. 2 plus 1 doesn't give us 4. So that's not going to work. We can try multiplication. 1 times 2 gives us 2. 2 times 2 gives us 4. First 2 works. That's good. 4 times 2, not 7. So for our pattern to work, it's got to work for the entire sequence, not just for the first couple. So we need to come up with another plan. Well, let's go back to addition. We saw 1 plus 1 is 2. What if instead of adding 1, what if we add 2? 2 plus 2 is 4. If we add 1 more to what we just added, 4 plus 3 is 7. I like that. 7 plus 4 is 11. 11 plus 1 more 5 is 16. Plus 1 more 6 is 22. Okay, so we've got our pattern. Now how can we describe that? Again, we can describe it in a couple of ways. One way we can describe it is just by saying, well, you add 1, then you add 2, then you add 3, and so on. These little ellipsis dots show that that pattern continues forever. Okay, or you can try to put it in words. This one's kind of difficult, but you can say something like add 1 more to the previous term than you added the last time. Okay, example 3. Skateboard shop finds that for 5 consecutive months, scales of longboards decreased. We've got a data set here. We've got the months on the left. We've got the number of longboards sold in that month on the right. Okay, we've got the first 5 months of a certain year. We want to use inductive reasoning to make a conjecture about the number of longboards the shop will sell in July. Okay, so we actually want to find, maybe help out this company and have them predict how many they're going to sell in July if this pattern continues. All right, so let's see if we can find a pattern. January, they sold 58. February, 55, down to 51, so it's decreasing each time. Let's see how many it's decreasing by. From 58 to 55, decreased by 3. 55 to 51, February to March, that's -4. From March to April, they sold 51 minus 48 is 3. They sold 3 less. And from April to May, they sold 4 less. Okay, do we see a pattern? So we've got -3, -4, -3, -4. We can assume that's gonna continue. So using our inductive reasoning, we want to find how many in July. So let's see, January, February, March, April, May, June comes next. So if we follow our pattern, -3, -4, then next up will be -3, 44 minus 3 is 41. We don't want June though, we want July. Okay, -3, -4, -3, -4. 41 minus 4 is 37. So, using inductive reasoning, we can conjecture that in July, this shop will sell 37 longboards. All right. All right, let's look at 2 more examples. Okay, 4th example. I want you to draw and describe the next term in this sequence. Okay, we start off with a circle. Then we go with a triangle inside a circle. Then we've got a circle inside of a triangle inside of a circle. So what's our next term going to be? Well, if we follow the pattern, then we should get a triangle inside of a circle, inside of a triangle, inside of a circle. Okay, example 5. Use inductive reasoning to find the sum of the first 20 odd numbers. Okay, we've got the first 4 given to us. So the first odd number is 1. By itself is 1. 3 is the next odd number. Add that to 1, we get 4. Next odd number is 5. Add that, we get 9. 7 is the next odd number. We get 16, and so on. So they give us the first 4, but they want us to find 20, the first 20 odd numbers. So we could just write out the first 20 odd numbers or punch them in our calculator and find that sum. That's not what it's asking us to do though. It's asking us to use inductive reasoning. So we want to look for a pattern and see if we can come up with a rule from that pattern, use that to find our answer. So let's look at our sums. Do you see anything unique? Do you see any kind of a pattern in these 4 sums that we have? So let's look at it. So this first one, that's when we have 1 odd number added together. This one is when we have 2 odd numbers. 9 is when we have 3. 16 is when we have 4. I bet some of you have already seen that these 4 numbers here are not only the sum of the first 1, 2, 3, and 4 odd numbers, but they're also the first 4 perfect squares. To get 1, well, 1 squared is 1. 2 squared is 4. 3 squared is 9. And 4 squared is 16. Okay, that's kind of neat. A different pattern, totally different operation, but gives us the same numbers. So we can conjecture that that same pattern is going to hold for any number of the first x odd numbers. So if we want to find the 20th, then first 20 odd numbers, then we can conjecture that 20 squared is going to give us that sum. So 20 squared, 20 times 20, is going to give us 400, which is the sum of the first 20 odd numbers as well. Okay, last term, counterexample. Okay, a counterexample to a conjecture is an example that proves the conjecture is incorrect. Now, with these conjectures that we're making, they're not always going to be right. They're kind of similar to a conclusion that's come from a scientific method or come from some kind of research. The conclusions aren't always right. They can be proven to be false if they are indeed not true. So, all you need is one counterexample to prove that a conjecture is false or incorrect. So let's look at an example here. Example 6 says, give a counterexample to the following conjecture. X squared is greater than x for any number x. Okay, we want to find just one counterexample. Now, in that last example we just did, for all those numbers that we squared, when we squared it, we got a bigger number. So I want you to find a number that you can plug in for x, that it gives you a smaller number than what you started off with. Okay, make sure you include that in your notes, and I'll check that in just a minute.